Okay, so recalling what we did in the last class, we've seen some more modern ciphers, block ciphers. Namely, we have seen uh, ciphers based in Feistel schemes. Anyone remembers one cipher which is based in Feistel schemes that we have taught? Like the data encryption standard, the DAS. There are other more modern ciphers. And then we talked about the advanced encryption standard, all the variants, how it was developed based on a request for proposals from the National Institute of Standards and Technology. And then we've seen how it works, and we talked about modes of operation for block ciphers. We've talked about the electronic codebook mode, which is the most natural approach, and we've seen that we should not use this mode. Why? Well, it's not safe, but it's not safe. Why?
Patterns, and if all the pixels are, for example, the same, the output is the same.
Exactly. Well, we've seen here, I've put the image, we've seen here the logo from the faculty, the original logo. When I encrypt with the advanced encryption standard in the electronic codebook mode, well, we get here a picture where well, the information is not completely, the image is not equal to the original, but you can get enough information to know what is in this picture. Okay, because you have pixels and blocks of white pixels, they will get encoding the same thing. Sometimes you can have a kind of patterns and not a solid color if the encoding of a fixed number of pixels is not exactly a multiple of the block size 128 bits. If it's, I know if it is like three bytes, a block of 128 bits is 16 bytes. So with 3 bytes, you don't get directly just a block. You just repeat after 3 or 4 blocks, and that's why you have a pattern that repeats itself on the green thing. Then we've seen other modes like the CBC mode, where we try to break this. We don't want that the same plain text is encrypted in the same ciphertext, so we do a kind of feedback. There are other modes. We've seen also the counter mode. There are other modes like the XTS mode for encryption of disk encryption and so on. I just want here to illustrate again. Sorry, I did a mistake and nobody at home told me because I'm not sharing the screen, right? Right now you are seeing the slides?
Yes.
Yeah.
Because I think before you were not seeing, right?
Yeah, that's true.
I was talking but well, okay, it's just reviewing what we did. I just want to also to exemplify in a little bit more detail the problems with the electronic codebook mode. I will just start here another Python program which you have available in 3 electronic. Just give me a few instances just to here I have another program, not the one that I've used to encrypt the image of the faculty. Actually, the image of the faculty, if you wanted, you could change the image and you could encrypt another image at your choice. This program is more or less similar. We are again using here the library Cryptography and the hazardous material. You are generating a random key with 32 bytes. That is the longest length for the key for the advanced encryption standard, 256 bits. And here I'm asking him to show the key. And then I have a plain text which consists of 4 blocks of 128 bits. That is blocks that can be fully encrypted with the advanced encryption standard. But they are the same with the zeros. And because when I initialize, it's just zeros. Then I do here the advanced encryption standard with some key that was with the key which was randomly chosen. I'm using again the PCB mode. Then I encrypt. Then I want to show the result of the ciphertext. And then, I will just execute this just to show. Sorry, it went to the other screen. So you can see here the result. I've asked you when you have this format X, I'm formatting in hexadecimal. That means that each block it's or if you want here the key is 32 bytes. Each byte can be written as 2 hexadecimal digits, okay? Because each hexadecimal digit is 4 bits. So to have 8 bits, 1 byte, you need 2 hexadecimal digits. So it's a way of having a more compact representation. And here, when you have 128 bits, you have 16 bytes. So can be represented with 32 hexadecimal digits. And if we see the result, so you have here the key, you can see seems perfectly randomly. Then I generated 1 block, 16, actually 16 bytes, which is 32 hexadecimal characters. Then all the blocks are the same when I encrypt with the advanced encryption standard. It is key what you get as in the ciphertext the blocks. Well, you can see that the encryption is exactly the same. Okay, so it's this thing that we are seeing in the picture. And here, just to see, well, I've decrypted in the same thing. Of course, I obtained the original plain text.
That is supposed to be a list
A list of
plain texts, like those zeros separated by spaces.
this is equivalent to 1 block. I'm putting here spaces because this is 1 block, which is fully encrypted with the advanced encryption standard. This is 128 bits. This is another block which is fully encrypted. So the spaces are basically to distinguish the blocks. Okay.
Can you show me the code again, just to see that? Understand how blocks were separated. Oh, it's in the plain text.
Yeah, it's here in the file.
X. Separated by
Here it
space.
is the number of bytes.
Okay, sure.
So
It's
if
to
you want, you
kill
can play with that.
it's to kill all the bytes. You declared in bytes parentheses 64. Like
Yeah, and declare all the bytes.
all the
Each
bytes.
block has 16 bytes. Okay,
Yes.
and so what I'm doing is in this plain text, I'm separating
Separate
16
16 by 16.
16
Okay.
bytes, and I'm writing the hexadecimal.
Sure.
So here we can see really that same input, same block will get same result. Okay. So that's basically the problem with the electronic code book. Any question, comment? If not, just to exemplify again these loans. If you use now the same thing, but exactly the same thing, the only thing which changes CDC, and typically you always use the initialization value, which should be random. And I think I mentioned, but wrongly in the last course, that you could avoid, you could not, you might use a constant one. I think I mistakenly told that, and that it's not true in general, because if you do that, we'll get problems that we will see in a moment. So in this case, if I run, I'm not sure if I said it or not, but I guess that the words I think I said, well, same thing. I have here a random key which was generated. I have the same plain text, but now you can see that CDC mode, despite the fact that the plain text are the same, the ciphertext are different. Okay, so just recalling here, you ensure with this chaining that with same inputs you get different outputs.
But it still would have given it was the same IP, right?
Sorry?
Still would have given the same different results for every block if it was the same IP.
Exactly. But let's see what is the problem of using the same IV. It means using a constant IV instead of a random one. Okay, I can encrypt several blocks with the same the same IV for each communication session, let's say. But it's good to change, and I'm going to show why. Let's open still another different program, which is I'm using the same initial value. Here I generate, I forgot to mention, but in the other one, see, I also had to generate an initialization value, which needs to have the same size as the block, as you can see here. The initialization value needs to be of the same size of the block, so it needs to be 16 bytes. So I generate random, I do here plain text, which is just zeros, and I do one which half is zeros, and another one it's just well, the other one basically it's just another C, which it's not zeros, also still zeros. And then I format again in blocks of 16 bytes, that means each block which is encrypted, and for each text. And now I encrypt both of them, and I see the result. And what we expect to see as a result.
I think it will be different still.
We'll see. Now I have plain text 1, just 4 blocks full of zeros, and I have plain text 2, which are full of ones. Okay, in hexadecimal, right? Now I encode plain text 1. You see each block is different from the other one. I encrypt ciphertext 2, and each block is different from the other ones. But there is a problem. What is the problem?
But ciphertext 1 is the same as ciphertext 2.
If we see
Almost the same.
the beginning of the ciphertext 1 is exactly, the first block is exactly the same, the second block is exactly the same, and the second block, they only change. Although the first block is different from the second one, they are the same for different, they only start different from the third block. Why? Because, well, the original first blocks are the same, only after the third block they differ. If you see here what happens, use the same initial value, the initialization vector. If P1 and P2 are equal, if you have a message where the first blocks are equal, ciphertext will be equal at the same. And it happens often that, for example, when you start to encrypt a message, you have a common header or something like that, which is similar for all messages. And, well, as you can see, you can obtain here some information like knowing that the two messages start with have a certain portion which is equal if you do not change the initialization vector and start from the beginning of each one. Okay? If you already have an ongoing session, even if you have P1, P2, and then again you have P1, P2, the result would be different because you are chaining everything. The problem is that if you start with P1, P2, and you start chaining with the same value, initialization value, this is a problem.
So that I see that kind of loses its purpose because if you put the same value always, that's why there's an I. Okay.
Any questions, comments, especially at home?
The examples are awesome. Really shows the differences.
I hope they clarify the idea is this one if you want to play with the, well, I put the source code so that if you want to play or somehow be my guess, the programs. Here I'm going to talk about, you might think, well, okay, I have, you can see, well, we have several problems when doing cryptography. First, we have the cipher can be weak, as we've seen with the shift ciphers, as we've seen as monoalphabetic substitution ciphers, as a Vigenère cipher, all of them can be broken. Then you have ciphers that, at least as far as we know, and there is more than 20 years, they cannot be broken, like the advanced encryption standard. But if you are not careful in how you use it, for example, using the electronic code book, then you can break it. And even on modes which can be safe, you have to do exactly, everything should be as intended. And sometimes you might think, oh, just changing this small thing, which is a minor thing. For example, putting constant initialization vectors. There are instances where that happen in software, and then you break all the security. What seems a detail sometimes makes all the difference, even in a secure, or what was a secure implementation or a secure algorithm. I'm going to show four types of attacks that can be used if the cipher is not well designed, or several details from the cipher. Okay. So as you can see, and there are other attacks even more powerful, like differential analysis and so on. I'm not going to talk about all of that because it's more complicated, but these are simpler attacks. But it's just to stress that implementation details, this is something that we must be very, 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 very careful. So typically always use things that were already implemented by specialists and don't do things by hand, don't try to implement the advanced encryptation standard alone, just use a library which has it or some program which already implements, and it was already reviewed by specialists. It was also designed by specialists. So the first attack, which I should have used, should have ordered the slides differently, already correcting for next year. Code book attack. I mentioned that when we have block ciphers, we have several parameters which are important for security, namely the block size and the key size. And I mentioned that if the block size is too small, these type of ciphers can be attacked. And notice, this is not something which is about the algorithm. It's any block cipher which is a block size which is too small. And how does it work? Going to provide here an example with the 16-bit block cipher. But with the 16 block cipher, here I've written perhaps in a different way, but imagine that you have some previous messages and imagine that you know what was the original plain text, either because it was something that was secret for some time, but afterwards it became public, or because you were able by other means to obtain sets of some plain text that you were not able to choose and some ciphertext. Okay, let's even simplify this and perhaps use, instead of 16 bits, let's use 8 bits. I will perhaps just write just have to try to understand where I can start. White screen. Well, they keep changing and sometimes. Let's see. Let me try another thing. Sorry, I will. Return. I hope that you are seeing. Imagine that you have a cipher with blocks of 8 bits. Now imagine that you got some files, imagine can even be a picture or something like that, that you got some data, encrypted data, you know the original file, let's say, and it was still a relatively small file, like 100 kilobytes, that was encrypted with this in blocks of 8 bits. Okay, this file, what it happened? It was divided in blocks of 1 byte, another byte, another byte, another byte, and so on. And because you are able to see both the plain text and the ciphertext, you are able to see for example, if you have here block 1, block 2, block 3, block 4, block 5. Afterwards, since you are also able to see the ciphertext, you are able to obtain several blocks of pairs, plain text, ciphertext. Okay. In this case, you are able to obtain thousands of these blocks. Now, what I ask is, how many of different plain text blocks do you have for 8 bits? How many possible? Power of 8. 2 to the power of 8, exactly. How many is 2 to the power of 8? It's 256. Okay. So how many possible plain text do you have? 256 possible blocks. Now, if you have a message, and if you know what are the plain text blocks and the ciphertext blocks, well, for example, with 100 kilobytes, almost for sure you will obtain all possible plain text. So if you don't obtain all, you obtain almost all, almost for sure. So you will obtain the block with 8 byte with bits. What it gets, you get the next one, what it gets, and so on. You have, and what you can do with this, you can do a kind of a dictionary. That's why the name code book. You have a book. Now imagine that you have another message that you don't know what is the corresponding original text. Then what do? You get the ciphertext. Now you get the first block, the second block, the third block, fourth block of 8 bits. And now what you do? You just stored here 256 pairs, and now you just see each of these pairs. You try to see C1, what is the corresponding pair. You see what it is, and if, for example, it was this one, now you know, so the plain text was this one. So you use a kind of a dictionary book. You have all the possible codes, and then you don't even need the key, and then you just see what was here, the ciphertext, and you just see the corresponding original text. And so that's why you have a kind of book with all possible codes.
But those ciphertexts are random from a brute force, for example.
Ah,
They are a brute force.
No, this is not a brute force attack.
No, I mean, kind of it's a brute force in the block per block. No way.
No, let's
Or there's a dictionary like.
let's exemplified with a concrete example, but to make it more.
Maybe.
Well, I'm going to make smaller even. Okay. Imagine that we are working with blocks of 2 bits. Okay, it's really small, but the idea is the same. Right. Now imagine that I have a message that I got somehow, and I know that and I know the corresponding ciphertext. Okay, plain text. And imagine that I know that it is this. Okay. Now, how would I do the code book attack? What I do would be now I split the corresponding blocks since I know that it's a block of size 2. So I know that block 01 was encrypted into 00. Block 11 was encrypted into 10. 10 was encrypted in 01, and so on. And now I can do a code book. Now imagine if possible blocks.
It's like a block, it's a word.
Yeah, original or plain text. That's right. So I have the ciphertext, and here, since it's a block of size 2, what are the possible ciphertexts? I can have 00, 01, 10, or 11. Right? And now what I do? Now I see what was the corresponding original text. For example, the ciphertext here in the first case, when it was 0, 0 coded, what was the original text? It needed to be 01. So I have here 01. When the encrypted text is 01, what was the original text? 10. When the encrypted text is 10, the original text was 11. And finally, when the encrypted text was 11, the original text was 00. So I have a kind of a code book. Basically, I know if each one of these blocks here appears, then I know what is exactly the corresponding plain text, and I can use like a book to lecture. I guess sometimes it's need to do this. So, for example, now if I have, let's say, I now have the message which is completely different. I don't know what was the corresponding plain text. What do? I divide in two blocks 2 by 2, and now I'm go to my code book here, and I'm going to see what it is 1 1. What it is? Well, it's this case. The original text was 0 0. If it is 1 0, I'm here, so sorry. It's the next one. It's this case, so the original text was 1 1. If I'm reading 0 1 now, it should have 1 0. And finally 0 0 0 1. So I was able to completely decode the message. Okay. And I don't need the key. I don't even need to know how the cipher works. I just need to know that it is a block cipher. Okay.
Don't we need to know the number of bits the block has?
Yes, we need. But typically that is usually no. Because this is a typically public ciphers, and even if they are not public, well, typically by other means, espionage, etc., typically it's possible to know.
Okay.
So, and
It's like a translation.
so any question? So, for example, we could do the same thing. I exemplified well. It's a very simple case, block of two bits. But for example, in a 16-bit block, I could do the same. I could try to obtain a code book for all the possible blocks, which are 2 to the power of 16. And then for each of these block, I would write the corresponding each possible cipher text block. I would write the corresponding cipher plain text, sorry, which has 16 bytes. So the total size of the code book, I have the number of entries times each entry would be 16 bytes, which means 2 to the power 20 bits, which is 128 kilobytes. So if you think about it, if you have enough pairs, if you have enough plain text and cipher text, you can easily do one of these code books, and it doesn't take that much memory. What you want is to have a block size which is sufficiently big to prevent this kind of things. For example, with 32 bytes, how big would be the code book? Oh, you just need to do computations. If you have a block of size n, you have the number of possible blocks, and for each possible block, you have to store the bits of the corresponding plain text. And since we are working with blocks of size n, you have here the size of the code. For example, if we have 32 bits, we have which, if we wanted in terms of gigabytes, for example, yeah, we would need to have the code with 137 gigabytes, which, if you write in a disk, can take a little bit more, but it's nothing special. Okay. You just need it is a huge amount or a large amount of plain text and cipher text. Sometimes you might not have all, but if all possible combinations, but even if you don't have all possible combinations of all possible cipher text blocks, even if you have a significant part, you can already take not the code completely, but get enough information or useful information from that. Okay? Any question, comment?
Professor, a primeira hora vai acabar e não tirou a assistência ainda? O QR Code?
Ah, tem razão. Obrigado. Alguma questão sobre isto? Sorry, just going to, I was forgetting, and I thank Pablo for remembering me about the registering the presence. So I'll start with cyber security. Postgraduate degree in cyber security. Have everyone from the cyber security postgraduate degree already registered their presence?
Yes, I think.
Yes, going now for the masters in computer science. So now it's the masters in computer science. Has everyone registered their presence? I hope so. So let's continue. In a few moments, I will have to ask you again for registering your presence. So I've just shown you the codebook attack. As I mentioned, I was going to show you 4 types of attacks. So this one, I hope that it makes it clear that you cannot use a block size which is too small, or else you can just memorize all possible blocks corresponding for each ciphertext and plaintext. Of course, you need to have access to some ciphertext and plaintext, but quite often this is possible. Not all that one, but for some pairs. Now, let's move to another attack. So as you can see, and the idea here is to show that there are many, many types of possible types of attacks, and we need to be very, very careful. Now we have the meat in the middle attack. Or perhaps even before the meat in the middle, let's talk about the slide attack, which perhaps it's just let me. Just an instant. Okay. Just want to return. If you recall what we have discussed for both the data encryptation standard and the advanced encryptation standard, typically modern ciphers, at least symmetric ciphers, we have several rounds, and each round increases the security of the method. For example, here when we use in the advanced encryptation standard, when we use a key of 128 bits, we have 10 rounds, and we have the key, but we didn't use directly the key in each round. We use different keys, which are called round keys or sub keys, which are generated from the main key, but we use different keys in each round. You might ask why I don't just use the same key in all rounds. Well, the problem is this attack that I'm going to describe, slide attack. If you use the same key in each round, well, basically this will not be secure. Okay, that's why we need a case schedule for any block cipher that uses rounds. How does it work? Now, I'm just illustrating. This is in the notes. I don't yet have a slide. That's also a change that I'm going to do for next year. But imagine that you have here a cipher which, so just for simplification, that has 3 rounds. Okay, each round which is represented in the picture by the R, and there is associated a key, and it's using the same key. Now, imagine that I can find 2 plain texts such that plain text 1 and plain text 2 are connected by this relationship that P2, the second plain text, is equal to P2 is equal to the round function applied to P1. Right? If this happens because of the structure of this cipher, well, we know that at the end of the second stage, when trying to encrypt P2, I need to have the same result as what would be here in the third stage, because if I have here, I get P1 here I have RP1 because I applied that, which is the same input of here, and so the output here must be the same, and also the output here. If I apply it once more here, I get the cipher text for P2 is R from the previous input, which is C1. Okay, and when I get 2 of these plain text, I get what is called a slip pair. What is the problem with slip pairs? The problem is that if I can find one, typically I can get the key of which was used in the round. And if the round always uses the same key, I essentially broke the cipher. So just how do I obtain from the relation that P2 equal to R P1 the key? Well, it depends. It depends on the cipher, but typically it can be done. For example, in the case of the advanced encryptation standard, for example, imagine that we knew.
Não, se calhar da caixa, como ainda não ativei, que eu esqueci.
If we knew that what was the input here and the output here, well, this is a transformation which is completely deterministic. This one is deterministic and I can invert it. And this one I also know how to invert it. And basically, I can compute the result at this stage here. And so I know what is the input here from the add round key and what is the output. And so I can do here a simple computation. Which basically if at the end of this stage I get P1 with a bar, and after add round key, which is basically a short, I get P2. So I can conclude that P2 is equal to P1 short with the key. And now I can solve this in order to the key. How? Well, we already mentioned that anything, if you do a sequence of bits, if you do short with itself, you'll basically obtain a sequence of 0. So what you do is P1 short, you short at the left in both sides. And here this thing will be 0, and 0 short something will give this something, and so I can get the key. So basically, I can break this. The only question is, how do I get the split pair? How do I get a pair such that this relationship is true? So I can do it very simply. If I have access to plain text and the corresponding ciphertext, I can just assume that this is true. It's the relationship that P2. I assume that if I assume that P2, and I'm putting here the key, K to represent key. If I assume that this is true, then what can I do? I can extract the corresponding key, which I will call key P for plain text. Right? And if this is true, it's this relationship here, it's true, then the corresponding ciphertext will also have to satisfy this. And so now I test if this is true. If this is true, then I've found a key which works. Sometimes you may have false positives, so it's best to test with a pair of, or a different pair of ciphertext and plain text to see that it is correct. If it is not, we try again. And here, if this second condition is not true, then what I do, I try a different pair, P1, P2, and I continue until I find this, a split pair. And typically, we will see this when we'll talk with about hash functions. I typically need, if I have a block size of n, I typically need 2 to the power n minus 2. 2 to the power n over 2, not minus 2, pairs until I get one which works. So this allows to reduce from 2 to the power n the computational power to the square root. So, which is already a big improvement. Okay. Any questions, comments? So this is the second type of attack, and it shows, note that all the small things, all the details that we have mentioned here, for example, for the advanced encryption standard, having a block size of a block with an adequate size is important. Having different round keys is important. There are several things. All of them, if you miss one, you don't get a secure algorithm. Now, before I forget, let's again record the presences, since we are already at 7 o'clock. Now, this is for Master in Computer Science, was what was last open. You could register your presence.
Can you give an example?
An example of
Of the last one, because I didn't understand use of ciphertext. I mean, you can use the plain text, sure, to get the key, but I didn't understand how you can use the ciphertext to get it.
okay.
It was just with the short, and with the short, with P1 and P2, that could you call it? Sure.
Yeah, well, I'll try to give a simple example. Okay. Has everybody registered their presence? Master in Computer Science? Yes, going now. Postgraduate degree in cybersecurity. So please register your presence. Cybersecurity. Has everybody registered their presence? Well, and we assume that yes. So let's assume here a very simple block cipher, where what you do in the round key is basically you just do you just shore with the key. Just a simplified version. Okay. Let me just pick here an example. It's not, well, creating one is a bit more work, but imagine that you have something with 2 bits. Okay, also just to simplify. Imagine that now you have one pair which is P1 is equal to 0, 0. Okay. And now imagine that you have again 3 stages. Now imagine that you use the key 0, 1. Then you do the short, what will happen here? You'll have 0, 0. What would be the output of the second here?
0, 1,
0, 1. Then afterwards,
0, 0.
well, here it will be very simple because, well, it's small, but it's just to give the idea. Might not repeat. And now imagine that you know that 0, 0 is encrypted into 0, 1. And you get also two other information. You know that 1, 1 is encrypted into 1, 0. Okay. And you know that 0, 1 is encrypted into 0, 0. And you get this text, this plain text and ciphertext you got somehow. Now, if you know that, now let's say that you are going to test, is this a slip pair? That means, is it true that, let's assume that this is equal to R key 0, 0. Okay? Let's assume if this is a slipper, if okay. So I'm assuming that this is true. If this is true, then I get the key. What is the key? Well, basically this is 0 plus the key. So the key must be 1, 1. Right? So this is my tentative key. I'm going to test it. Now I have a second pair. Now I have another pair, 0, 1, 0, 0. Now I test. Is it the key? It is that. No, then I try to encrypt, and I encrypt 3 times. Here, I do one stage. I have, and I get that if I encrypt 0, 1 with this key, what would I obtain? After the first stage, I would flip both bits. I would get 1, 0. Then they would flip again after the second application of R, and then to get 1, 0. And then I'm going to check here, but I didn't got 1, 0. So this key doesn't work. Okay. What now I am going to do? Now I'm going to try another pair. Now let's try 0, 0, 0, 1. I do exactly the same thing. Okay. I assume that this is true. 0, 1 equal to R 0, 0. And then solving this, I get 0, 1 equal to 0, 0 plus, or the key is equal to 0, 1. And now I'm going to test if this is true in a different pair. Sorry. And now what am I going to see? I'm going to see if, sorry, I even did, I'm mistaken here. What I should see is whether the ciphertext is equal or not. For example, here, if I encrypt does this relationship holds? And I'm going to see does it hold or not? Or this pair with this key, I get the ciphertext. I should have 0, 1, which is the ciphertext of 0, 0, is equal R key 0, 0. Is this true for this key? Yes, it is. So this is a split pair and a very likely key, which I have to test with in another pair to see if it works. Here I apologize, I did it wrong here. I needed to verify that the corresponding text for 0, 0 and 0, 1, which would be, is it 0, 1 equal to R key 0, 0? Sorry, opposite. No, sorry. 1, 0, 0, 1. Okay, which was the first pair. I need to see if this is true. P1 is 0, 0. The corresponding ciphertext is 0, 1. And P2 is 1, 1. And the corresponding ciphertext is 1, 0. So I need to see whether this is true. And now I check, is it true? This implies that if the key is 1, 1, I should have that 1, 0 equal to 1, 1. It is true. Sorry, I must have made here a mistake. Just look. All right. Sorry, isn't it all right? I think it was the right one. On the key. 0, 1. And get the right result. Well, to be honest, here it should give a different result. It gave the same because here it's a very simple cipher. I think and we are talking with very small bytes. Well, as I said, it's not easy to get a very good example.
But I think I understood this basically the sliding effect. Like you test it out with the first plain text and then you
Yeah, and then
Yes,
you
with
obtain a
ciphers.
key, and then you see if the ciphertext relationship happens to be true. In this
True,
case,
yes.
as far it's true, but it's basically chance. It's a false positive, and then you need to test it another say. Well, here also it's because this is a very simple case,
Yes.
but
Be
you can
another
do this.
operation, right?
Sorry.
It could be another operation.
Yes,
In
it could be another operation. I picked
It'll be a lot more difficult.
the XOR to be simpler.
Easier.
Okay, and since it's only 2 bits, and but if I try to get bigger, well, it can be done, but it takes more time.
Yes, yes.
Okay.
But it's understandable still.
Okay.
Thank you.
Well, any questions at home? Well, if not,
Sorry, Professor, just to confirm. So it seems the key is 0, 1. That was the
Yes.
conclusion.
yes. The conclusion was that it was 0, 1. Although in this simple example, which I invented here in
Okay.
well in place which I was not expecting, Well, this is too simple, and you get fake, false positives.
results.
So you get false results
Uh,
easily. So
Yeah, not sure if it takes a little bit of time, but I just don't understand why you say false positives, because apparently the checking that key with the results seems to be correct. So I might be missing something and not understanding why it is a false positive.
I think it's because the results are a little bit too simple. The information we knew was a little bit too much, wasn't it?
let me just look carefully. Just to zero. It was a bit by chance, but you could see that it's not. But actually, how we did before, it was enough. I was using the code, which is which avoids the false positive. If I really encrypt, now if I obtain that the code is 1-1, what would I obtain here in above? I would write, which was what I was trying to. I would ask. I would start with 0-0. If the key would be that one, instead of focusing on this relation, I could really see if the result of the encryptation with this key is correct. I would get 0-0. Then after this stage, if I add the keys 1-1, what would be the result at this stage here? It would be 0-0 XOR 1-1. So it would be 1-1, right? In the next stage, it would be 0-0. In the other stage, it would be 1-1. And it's not the same result as we wanted to have. So this one would not work. I could test in this way. Okay? For this simple example. And see that it. And the other one, you look using this relationship. Well, since this is a really example, this gave a false positive. But if you do for the whole cipher, it's another way of checking if it is a split pair or not. You can see that the key that you obtain, it's not correct. Okay? But in the second case, it works.
Yep. Yeah, yeah, totally right. Just one thing that I'm not sure if I'm understanding correctly. It's the name of the pair is slip.
Slid.
Slip.
I will write.
I couldn't find the word.
Slid.
Okay.
Yeah, well, this is called slide.
Yeah.
Okay. And then you just remove the last e. I don't know why it is called slip pair, but if you see in the literature, it's what they call.
Okay. Thank you.
Any more questions? So we've seen second attack. Let's see a third one, which is the meet in the middle. Perhaps I will write here again. There is an algorithm way which is called DAS. As we mentioned, the DAS algorithm, the data encryptation standard, it's no longer safe. So some people, to make it more safe, they thought instead of, what should I do? I have a plain text and I encrypted once with dash, I use one key, which it's 64 bits, but because I have 8 bits of parity, in reality it's just 56 bits. Then I pick the result, I encrypt it again with this. Now with the second different key, another 56 bits. And now I encrypted a third time with this. And now I get the output of this cipher. Because all the keys are different, I might think that this is the same as having a key of size I could think, well, I have a key of 168 bits. I break the key in 3 parts, and then yes, I was just here if I was doing the computation correctly. It's 168 bits. I break it in 3 equal parts, and each part is fed as a key to the DAS. And you might think, well, perhaps I increased the strength of the key from 66 bits to 168 bits. But unfortunately, this isn't true. You only get 112 bits of security. And why do you get only 112 bits of security? Because of this attack, the meet in the middle. And actually, the 3-, it doesn't work exactly like this. There is a small variant, but just to mention, here it's encryptation. Here it's also encryptation, but here it's not encryptation, it's decryptation. And it's decryptation, why? Because sometimes for compatibility reasons, we want this to be compatible with the original data encryptation standard. And in this case, if you use K1 equal to K2 equal to K3, well, this is just the standard test. Because if you use the same key everywhere, and here it's decryption, here you encrypt, then you decrypt, you just get P again, and then you encrypt. Okay, but sometimes it's convenient for legacy reasons that you are still able, without changing hardware, if this is done in hardware or software, that you can do it. So there is this trick of using decryptation, but which does not make the algorithm weaker in the middle, instead of encrypting. But again, this only has 112 bits. And why is this? This is basically because I can do the following attack. Imagine I'm going now pick the dash. Imagine that I encrypt twice. I do dash with one key, 128 bits, and then I encrypt a second time. I have plain text corresponding ciphertext. Again, here 56 bits. Then what could an attacker do? Well, it could trade computation time for memory. What you would do is, first, you would imagine that he knows a pair plain text, ciphertext that he obtained somehow, right? And now, what does he do? Computes for this plain text that he knows, it computes the output of one single application of dash with all possible keys K. Okay? and he makes a table with the results. How many keys I can have? If it is 56 bits, how much time do I take to do this? I need to test all the keys, how many keys there are. 2 to the power of 56, okay? So I spend time to the power 56. I get, and I store the results. This is where the trade-off is, trading memory, time by memory. And I can sometimes store more efficiently. Now what I do, I pick the ciphertext, and now instead of encrypting, I decrypt. And I also do for all possible tests, all possible keys, I'm sorry. How much time will I take to do this? How many keys are there possible for C? How many possible keys can I use in the decryption algorithm?
The same?
It's again the same thing.
Okay.
Okay. So what is the total amount of doing this amount of doing these two calculations? It's doing first for encryptation and then decryptation. Okay. And then what do? I get two big tables, and then I go to check for each key, each position for the same key in one size and the other. I'm going to see if the things agree here in the middle. Okay. If they don't agree, there is a is that here if you encrypt it, you get a partial result M. That should be the result of encrypting by P here, and it should be the result of decrypting by C, and it should be common. So here I'm trying to have common entries, okay? And then when I have a common entry, what do I see? I see what was the corresponding key 1 and key 2 on the table, and I register. And now I test these two keys again, another pair of plain text and ciphertext. And if the encryptation works also for this pair, then it is very, very likely that it is correct. If the text for key 1 and key 2 don't agree, then I test another key, another pair of keys, and so on. How much time it took me? Well, it took me this amount of time. Well, it's to the power of 57, but well, it's more or less of the same order of 256. But since I had two keys of 56 bits and 56 bits, I hoped that the total security would be 112 bits, and that in total I would need, with brute force, 2 to the power 112 bits, which is much higher than the real security of this method. Okay, so and this is the name meet in the middle, because I'm really trying to meet in the middle. Okay, and the same idea can be used, returning to the 3 dash, for the same thing. Here simply instead of doing partial, I would do one partial here. I would test all possible K1s, and then I will do this part and would do decryption here and then encryption, and I would test all possible pairs of keys, which here would be the equivalent of 112 bits. And so when I try to meet in the middle, it will be the bigger quantity between these, and here the bigger quantity is 112 bits. So that's why we get only 112 bits of security. Any question of common? If not, we are going to the last type of attack, which can defeat things like the chain, the advanced encryptation block standard, the encryptation, the advanced encryptation standard, even if working, for example, in cipher block chaining mode. Okay? And how does it work? Well, I'm going to use also a picture. It's the so-called padding oracle attack. I also don't have a slide, sorry, I'm going to put one next year. Imagine that you have here the scheme for decrypting the one cipher in CBC mode. Okay? This is the correct scheme. Now imagine that you are, for example, you have a server in the internet, and then you send it some what is ciphertext. This server is going to decrypt, and it's going to use this text for something. Maybe you don't have access to the decrypted text, but you know that the server is decrypting. Sometimes there are warnings by the servers that a certain type of error happened, and then it warns you, oh, there was this error, the message didn't get there, or completely, there were missing blocks, or it was badly formatted, and so on. If that happens, depending on the type of error, we can explore that information given by the server, which is a so-called. It seems that it is minimal information, but it's enough to break the cipher. I'm going to show how this works. First of all, it explores the idea of how the padding is used. I'm just going to, first of all, describe how the padding works, or at least there is various ways of doing padding. We have this standard, for example, which is quite well used. It is here described in the course notes, more detail. But actually, for some reason, it's not. Assuming that basically, if the block is divided into bytes, it works as follows. I'm going to assume here this padding. If you have a block, which, for example, in the advanced encryptation standard is 16 bytes, and here we divide in bytes, what do? If there is one missing byte, I'm sure that it was here in the. It's simpler if I show.
Sorry, what was the name of this attack again?
Padding oracle.
Padding oracle attack.
Thank you.
Sorry, I just want to locate. I think it's better that I locate in the notes, because I have put it there. Yes, here it is. think it's better to show you in the notes because in case you want to find, you can have more information. This standard, well, in case of blocks with 16 bytes, as I was mentioning, 128 bits, this works as follows. If you have a block, remember that if you don't have exactly the message is not a multiple of the block size, that is 16 bytes, you need to add things, which is the padding. If there is only one missing byte, you add 0, 1 in hexadecimal, which corresponds to 1 byte, right? Just to say, well, there is 1 byte missing. If there are 2, you add 2 extra bytes, 0 in hexadecimal notation, and so on. The only thing, and if there are 15 missing bytes, then you add 15 bytes, 0f, where f in hexadecimal is 15. Okay. The question is, what happens if the block is exactly 16 bytes? Well, in this sense, it's not in terms of efficiency, especially for small messages, not the most efficient, but basically you add a full block of 16 bytes, 1, 0, which is saying 16 bytes missing. So if you read that again, you know how many blocks there are missing. Now let's return to the attack. I have this block. I'm going to just write this in. Now, so just write the new one. Sorry, I'm just putting the scheme for decryption. So now I have here the scheme. Now imagine that you are an attacker and you receive or you capture this ciphertext. Let's imagine that it's just 3 blocks, just to exemplify. Okay, C1, C2, and C3. Each one, let's say that we are talking about the advanced encryption standard, so each one is 16 bytes. Okay, let's just assume this. And I don't know what is the plain text. I want to decrypt this, but I know that there is a server which decrypts, it knows the key, and it tells me if the padding was well formatted or not. It gives an error. Was not well formatted, the padding. So what I do, each of these blocks, it's 16 bytes. I'm going to write C0 for the first byte, C1, and C15 for the last byte. Okay? And here also for all the blocks. Okay? Any question up to now? So I'm going to start to decrypt the last block of C3. How am I going to do that? I'm going to, I have access to C1 and C2. I'm going to send to the machine, to the server, the same message, C1, C2, and C3, but I'm going to change the last byte of C2. So what basically I'm going to change is C2 15, and I'm going to change it. Okay? And so I'm going to change what will the machine receive. The machine will receive as the last byte. It will decrypt here. C3, okay? So after, I don't know how I represented this in notes. Yeah, I explained here. Well, decrypted. So I'm going to decrypt the last byte of C15. Well, I'm not going to decrypt, it's the server which decrypts. I'm talking about the server, but it's something that behaves in this way. What it is going to do after decrypting, it is going to make a sure with the last byte of C2, which I gave him. Do you agree? This is from the scheme here of decryption. Is it okay? I'm just writing down things. So first you have C3 decrypts, you get this part, and then it does a XOR with the input that it gets here. I'm working byte by byte. Right. Okay?
In the 15 version. Okay.
And now imagine if this by chance yells 01, what is this? This is a valid formatting, assuming that I'm using this PKCS #7. Okay, this is a valid formatting. So, and the system does not provide any error. So I know that since I know this value, what can I do? I can write solving in order to this quantity, basically by doing XOR of this thing at the right at both sides, I get this. Since I knew how much was this, I can decrypt the last bit. If this was not 01, what will the system tell me? There was an error. The padding was not well formatted. And then I keep getting errors, and I keep changing this bit until I succeed. How many tests I will? How many bits? How many bytes I will have to test until I succeed? Typically, you have 256 bytes. Typically, I will probably, on average, have success on how many bits? With how many attempts? If there are 256 possible bytes on average, no, I will succeed on average with how? Okay, so 128.
Worst case scenario.
So on average, I will succeed 128. Then I already was able to decrypt the last byte of C3. Now what I am going to attack is the previous one. Now I want not the last byte of C3. So I already have decrypted this byte. Now I want to decrypt the previous one. Now, what do I do? Since I already know what is this value, I can change. I can now pick a C2/15 so that when decrypted, this is 0.2 because I already know what is this is. Now I already know the decrypted text, sorry. So I can choose one of these values so that this is 0.2. And now what do? I do basically the same thing, but now instead of using this value to extract this value here, now I'm going to use this value to extract this one. And how do? I try to obtain the same equation. Now what I want is, sorry, here it's K, dk I know that the padding in this case will succeed if this XOR C2 4, since this basically says, this condition says that there are 2 missing bytes, it only succeeds if this is 0.2 also. So what do? I test different bytes here until I succeed. And when I succeed, I can get the decryption of this is 0.2. Sorry. Well, this is committal, so it's not a problem, but so I can do this until I succeed, and then I manage to obtain 1 more byte, and then I can keep doing with this scheme. And how much time did I obtain? How many tries I had to do to get to succeed here? Well, again, 128. Okay. If I have 16 bits, how much time I needed to decrypt a full block? Well, I have 16 bytes. On average, it took me 128 bits. So I need this amount of time to decrypt on average a block. And how much is this? Well, it's 16. It's 2048 attempts per block, which has 128 bits. But I want that the best attack is brute force. And what is brute force? It's this. So I get a big improvement. And okay, it's not at the first time, but it's something which is feasible. So something that I should not give is any information about whether the padding was well formatted or not, because even this very apparently inoffensive information can be exploited to break. This was not an obvious attack in the beginning, it didn't appear, but there were some authors that after some years, they recalled it. They imagined this attack, and as you can see, it can be quite powerful. Any question, comment? Well, if not, I'm going to finish class here. Have a nice weekend and see you next week.
Thanks.
Nice weekend.
Yeah, you all. See you next week.
Yeah, profits, man.
Bye.
See you next
Bye.
week.
See you.
See you next week. Bye.
Goodbye.